Hey guys, what's up? We're going to look at the principle of moments. So what is the principle of moments? Well, it tells us about things in equilibrium. And in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. We can write that mathematically like this here. This symbol here is sigma, and it means the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. And we must remember that moment is equal to force multiplied by perpendicular distance to the pivot. The best way to understand the principle of moments is to do some practice calculations. We're going to do lots of those. The first one is a question where we've got a beam and we've got some weights, and we know the distances to a pivot, which is here. And the question says, is this system in equilibrium? Well, in equilibrium, according to the principle of moments, the sum of the anti-clockwise moments should equal the sum of the clockwise moments. Before we jump into this question, the best thing to do is check that you've got all your distances labelled, and that you've got everything in weight rather than in mass, and that you've labelled clockwise and anti-clockwise moments. So our distances are sorted, everything is in newtons, but now we just need to label clockwise and anti-clockwise moments. This here is a clockwise moment, because if you think about the pivot, the weight of this object is going to make the beam rotate clockwise. This also is clockwise, and this one here is going to cause the beam to rotate in the anti-clockwise direction. Now we just do some basic maths. We use the formula moment is equal to force times distance. And we have to do this for all the clockwise and add them together, and all the anti-clockwise and add those together. So in the anti-clockwise direction, we simply have 11 multiplied by 6.5 is equal to 5 multiplied by 2.5 plus 7 multiplied by 7. So we get 71.5 is equal to 12.5 plus 49, and that gives us 71.5 is equal to 61.5. Those two numbers do not equal each other, so this system is not in equilibrium. And that's important. We've used the principle of moments to show that this is unbalanced. The anti-clockwise moment is much greater than the clockwise moment, therefore this beam will rotate in the anti-clockwise direction. It is not in equilibrium. Now we've got a system that is in equilibrium, and we've got to calculate this distance x such that this system is balanced and it's in equilibrium. Once again, we use our principle of moments. The sum of the anti-clockwise moments is equal to the sum of the clockwise moments. All the distances are labelled, and we've got all of our objects given as a weight rather than a mass. So all we've got to do is label clockwise for these moments here, and anti-clockwise for these moments on the other side. And now it's just simple maths. So we do each of them in turn. 20 multiplied by 1.2 plus 25 times 0.9. Got to make sure that we don't use centimeters. We always use meters. Is equal to 15 times 0.3, because it's 30 centimeters, plus 20x. So that leaves us with 46.5 is equal to 4.5 plus 20x. And now it's just basic algebra. So we take the 4.5 over to the other side, and we get 42 is equal to 20x. So x is 42 over 20. And that gives us a value of x of 2.1 meters. So just by applying the principle of moments, we could work out the distance that this weight had to be from the pivot for this system to be in equilibrium. And we always follow the same method. This next one is a little bit more tricky. We've got to calculate the tension in this string for the system to be in equilibrium, but the string is acting at an angle. So before we do anything, let's just have a look at the problem. Here's our pivot at the middle. We've got a mass here, so we want to make sure that we convert that to a weight. So weight is 100 times g, and remember that g is equal to 9.81. We've got another one here, so that's going to be weight is equal to 350 g. And now we've got this tension in a string, and it's acting at an angle. We don't like things acting at an angle, so we're going to resolve it into its horizontal and vertical components. The horizontal component is going to be t cos 50, because we're going across the angle, and the vertical component is going to be t sine 50. Now we have to consider which one of these components are we going to use, and it's going to be the vertical one, because the line of action of this force is perpendicular to the pivot, so we can ignore the horizontal component of this force for this question. Now that we've labeled all of our forces and we've resolved this tension into vertical and horizontal components, we need to consider which is going to be clockwise and which are going to be anti-clockwise moments. On this side, this is going to be a anti-clockwise. This weight is going to be a clockwise moment. And this tension, this vertical component of the tension, is going to cause it to rotate in the anti-clockwise direction. So it's really important we label them. Next, we write the principle of moments. Sum of ACW moments, anti-clockwise moments, is equal to the sum of the clockwise moments. So now all we have to do is solve the problem. So we get 100 times 9.81, which is G, multiplied by 5, plus T sine 50 times 8 is equal to 350 multiplied by 9.81, which is G, times by 2.8. And on this side, we get left with 4,905 plus 8t sine 50 is equal to 4,700 and, no, sorry, is equal to 9613.8. So we've got to take this to the other side and we get left with 8t sine 50 is equal to 4708. Therefore, the tension is equal to 4708 divided by brackets 8 sine 50. And that leaves us with a value of tension of 768 newtons. I've rounded it to 3 significant figures. So once again, all we've done is follow the principle of moments. The sum of the anti-clockwise moments is equal to the sum of the clockwise moments. This next one is a real life example, so I've shown it as an actual application to a real life problem. What is the distance x such that this crane system is in equilibrium? So the crane has got a counterbalance, which is over here, and it's trying to lift up a sort of like an iron girder, which has got a mass of 250 kilograms. So, but the, I should also say before we begin, but the crane itself has some mass. The bar has a mass of 100 kilograms, and that's going to create a moment about this point here. Here's our pivot P. So we've got this one as a weight, which is good, and that one's going to be an anti-clockwise moment. The weight is going to be 100 times 9.81, or 100 G, and that's going to be a clockwise moment. And the steel girder has got a weight 250 times 9.81, and that is also going to be a clockwise moment. And we want to know what's this distance x. So as always, we always use our principle of moments, where the sum of the anti-clockwise is equal to the sum of the clockwise moments. So we can simply say 30,000 x is equal to 100 times 9.81 times by 3.2 plus 250 times 9.81 multiplied by 6. And we get left with 30,000x is equal to 17,854.2. So x is simply 17,854.2 divided by 30,000. And we get a value for x of 0.6 meters. So very simple. Every single time you follow the same steps, the same method, and you cannot go wrong. I'm going to keep going through more examples because the more you see, the better prepared you'll be for those in the exam. So question 5, we've got a shelf here. And this is a uniform shelf. This is a really important word, and we'll come back to that in a minute, which has a mass of 12 kilograms. So 12 kilograms here, which means that it has a weight of 12 times 9.81. It is attached to the wall by a screw. So there's going to be our pivot. And it's got a string which is holding it up, which is at an angle of 50 degrees to the shelf. And we've got to calculate what's the tension in the string for this system to be in equilibrium. We haven't got all of our distance labeled on our diagram, but we know the overall shelf is 25 centimeters, and we know the distance from the string to the end is 2. Therefore, we can say that this distance is 0.23 meters, because we always use meters. And because it's a uniform shelf, the center of mass must be halfway along. So this distance is going to be 0.125. So we've got our forces, we've got our distances. Now we need to consider the moments. The weight is going to provide a clockwise moment about the pivot. And now we've got this tension, but it's at an angle. So I want to resolve it. And we're going to use the vertical component T sine 50, because the line of action of that vertical component is at 90 degrees to the pivot over here. So this T sine 50 is going to create an anti-clockwise moment about our pivot P. Next, we write down our principal of moments. Sum of anti-clockwise moments is equal to the sum of clockwise. So this is where we go for the anti-clockwise first. T sine 50 multiplied by 0.23, and all of that is in brackets, is equal to the mass, which is 12, times 9.81 to get it as a weight, a force, multiplied by the distance, 0.125. We're always working in meters, never centimeters. So 0.23 T sine 50 is equal to 14.715. Therefore, we can simply work out the tension by doing 14.715 divided by brackets 0.23 times sine 50. And that leaves us with a value for tension of 83.6 newtons. Really simple. Okay, here we've got a suitcase, and the suitcase has a weight of 20 kilograms, and the pivot is going to be this point where the wheel touches the ground. Here's our pivot. So the weight is actually going to provide an anti-clockwise moment. And we've got a person carrying it with some tension T, but we don't like tension at an angle, so we want to resolve it into its horizontal and vertical components. This will be T sine 30, and up here this will be T cos 30, because I've gone across this angle here. We're not interested in the horizontal, we're just going to look at this vertical one because the line of action of this is at 90 degrees to our pivot P. We've got everything almost sorted. We've just got to remember that this is a mass, so we need to use the weight, which is 20 times 9.81. We're not going to use the mass, we're going to use the newtons, the weight. And we've got to remember that we've got these distances in centimeters, and we always want to convert to meters. So we always start every single one of these problems with the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. We've only got one anti-clockwise moment here, and it's this one here. So we've got 20 times 9.81 multiplied by 0.05 is equal to the clockwise moment, which is T cos 30 multiplied by the distance, 0.55. So 9.81 is equal to 0.55 T cos 30, and we can therefore simply write that T is equal to 9.81 divided by brackets 0.55 cos 30, and we can calculate the tension to be 20.6 newtons. Simple as that. Okay, last couple of examples now, because I know we've done a lot, but it is really important that we see a range of these different problems because they've all got slight differences and nuances to them. This is a little schematic of someone's arm. So this point here is the pivot, and that pivot is your elbow. We've got a muscle, which is providing a force, and we've got the weight of the arm. The arm weighs about 1.8 kilograms, so the weight is going to be 1.8 times 9.81. And we've got this person holding a 5 kilogram mass, so that's going to have a weight, which is 5 times 9.81. Okay, so we know where our pivot is. We've got all of our distances labeled, and we've got all of our forces as forces, and we're not going to use masses. So now we need to consider which are going to be clockwise and which are going to be anti-clockwise moments. Well, the weight of the arm is going to be clockwise. The weight of the mass in the hand is going to create a clockwise moment, and the muscle is acting in the opposite direction, and that's going to provide the anti-clockwise moment. So we write our principle of moments. Sum of anti-clockwise moments is equal to the sum of clockwise moments. We've only got one anti-clockwise moment, and that is the force here. So we say that F multiplied by 0.03, because we're using meters, is equal to 1.8 times, we're looking at this force first, times 9.81 multiplied by 0.17 plus, looking at this moment now, 5 times 9.81 multiplied by the distance. Now the distance is 17 plus 18 centimeters, which is 0.35. meters. And we get left with 0.03 F is equal to 20.169. Therefore, F is simply 20.169 divided by 0.03. And that leaves us with F is equal to 575 newtons. So it's a large force. The reason why I need such a large force is because the distance from where the muscle joins onto the bone is a very small distance to the pivot. So a smaller distance means you need a larger force, whereas the mass is only 5 kilograms. Therefore, it's a small force, but it's at a much greater distance. It has a larger moment. The final one is this, and we've got two columns. So we've got column A and column B, and we've got a large plank of wood, which has got a mass of 250 kilograms, and it's balanced on those two columns. It's in equilibrium. We want to calculate the normal contact forces F1 and F2 provided by the columns. And we're going to use the principle of moments to do this. And we've got two different pivots here. We could take a pivot about A or B. I'm going to choose A. So we're going to say about A. Before we begin, we're going to just make sure that we've got everything set up. So we've got all of our distances, and we've got the weight, which is going to be 250 times 9.81, because we always look out for masses and make sure that we're converting them into newtons by multiplying by the gravitational field strength. What's important is if we take it about A, F1 has no moment because there's no perpendicular distance. So we're going to now do the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. The weight is going to provide the clockwise moment, and F2, the normal contact force as a result of column B, is going to provide an anti-clockwise moment. So we can say F2 multiplied by its distance to the pivot, which is 1.3 plus 0.6 times 1.9 meters, therefore, is equal to 250 times by 9.81 multiplied by 1.3. So we get 1.9 F2 is equal to 3188.25. So F2 is simply 1678 newtons. Now, if I wanted to work at F1, I could simply take the pivot to be point B and repeat the process. But I know because this is in equilibrium, the forces up have got to equal the forces down. Therefore, F1 plus F2 must equal the weight. So I can say F1 plus 1678, which is F2, is equal to the weight, which is 250 times 9.81, which is 2,452.5. Therefore, F1 is simply 774.5 newtons. I want to re-emphasize, I could have just done moments about B and repeated the process, but this is a little bit quicker. So there we have it, lots of examples about how we use the principle of moments. Let's just summarize everything that we've done so far. The principle of moments says that in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. And that's what this mathematical expression here means. And you should start every single moments question by writing that down. Some steps to remember. Number one, label all the forces on the diagram. And remember that weight is mass times gravitational field strength. We never use masses. Label all the distances to the pivot, and you want to use meters, not centimeters. Then you want to make sure that you've labeled the moments, whether they're clockwise or anti-clockwise. Remember to resolve any forces at an angle, and you only use the component that is perpendicular to the pivot. Finally, you then simply use the principle of moments, that the sum of the anti-clockwise moments is equal to the sum of the clockwise moment for an object, for a system to be in equilibrium. If you follow those simple rules, you can't go wrong. That's it. Thanks for listening. See you all soon.